So I did not finish all of these things. Recall, we did some of these structures. I'll leave it to you to deal with drawing resonance structures for that and some of the others as well. All right, where did we leave off? Not there. Right here. Okay. Localized versus delocalized. These terms get used a lot. When we talk about resonance, the word delocalized is often generally used as a synonym. It's not really, they're not synonyms, but we say electrons are delocalized when there's resonance, or we say charge is delocalized when there's resonance. Okay, so that means it makes it more stable if you can move electrons over multiple atoms or formal charges over multiple atoms. That's what you're trying to do here to make this more stable. Okay, so to figure that these are delocalized, electrons have to be in an unhybridized p orbital. And it has to be able to overlap with p orbitals on neighboring atoms. Also, to be delocalized, electrons must be on an sp or an sp2 hybridized atom. Now, technically, they could also be in a lone pair. Okay, so lone pairs on sp3 are also okay in some cases. For example, if we think about this, this is the first pattern I think we looked at, right? We are moving electrons from an atom of the lone pair here over to here. And ultimately, this creates another contributor. Which is more important, the first one or the second one?
The first one.
The first one.
Yeah. They all have, they're both good in that they have full octets. But the only problem here is that with this one right here, there are formal charges, whereas the one on the left, there are not. Okay. What hybridization do we predict for this nitrogen?
sp3.
Good, but what is it over here?
sp2.
It's sp2, right? So you see, there are cases where it's ambiguous because of resonance. It's sp3 in one resonance structure, sp2 in this one. Same idea up here. Here it's this oxygen is sp2, here it is sp3. So it's almost kind of like in between, so to speak. It would be better to probably talk about all of them as sp2, even though it looks like it's sp3 right here. So that's one of those cases where the rules don't always work out exactly the way they are. It's more sp2 than sp3 because of resonance. Its resonance structure allows that. Okay, so that's what I was just saying right there. So because of delocalization or resonance, sometimes things that we predict to be sp3 would actually be sp2. And resonance is the primary reason for that. So we already talked about that this is sp3, but it really couldn't engage in resonance if it was really sp3. This is really more sp2. And what shape would it more likely have then if it's sp2? It's more trigonal planar, and these electrons are delocalized instead of the electrons just being off in a plane all their own. Okay, so in an amide, the nitrogen is sp2. And so it's better to think of an amide as like this. If we have an sp2, all of these atoms are sp2, they all have a vacant p orbital, except for the nitrogen. Remember, we said it's not vacant here. And actually, I'm sorry, these aren't vacant. The pi bond is right here. So we have a pi bond between the oxygen and a carbon. We have the lone pair nitrogen electrons, which instead of being in a hybrid orbital, are better thought of as being in a p orbital, and they're all being moved around. So we say the electrons are delocalized. Delocalized. Remember all that talk I did earlier on about conjugation, alternating patterns of single and single double bonds. That's when you have all these p orbitals next to each other. And when you have this kind of a pattern, it is much more stabilizing. And that's why we would say the nitrogen should probably be considered sp2 and not sp3. It's not always easy to recognize that. And so it's by experience. If I were to ask you about this, I've asked this before, and I don't ask it like, you know, tell me the hybridization, and then you say sp3, and I go, ha ha ha, you're wrong. What I'll usually say is, if I ask about this, I'll say, it looks sp3, but it's really sp2. Why? Okay. I fully expect people will forget that this nitrogen breaks the rules. But when you think about resonance, there's a reason that it should. Let's look at another example, and we'll really focus on these next examples next semester, but it's important to kind of look at them in advance. And that is this molecule right here, pyridine. Pyridine looks a lot like what molecule that you should already know?
Aromatic.
Yeah, and the name of that aromatic was benzene, right? The functional group is aromatic. We will learn later that pyridine is aromatic, but we haven't defined why yet. Okay. It's also a what functional group? It's a nitrogen bonded to 3 carbons, so it is an amine. It's a type of an amine, right? It's in the amine family, if we think about it as being like that, meaning it's going to be basic. Okay. If we look at delocalizing the electrons here, in theory, we can push these electrons, but you can't do this. You can't do it on this molecule. Why? Well, it turns out that if we think of this nitrogen, its lone pairs are outside the molecule. Because if the nitrogen is sp2, which it is, you agree this has to be sp2. It's bonded to 2 atoms, has 1 lone pair, has to be sp2. What are the sp2 orbitals doing? They make sigma bonds and they hold lone pairs. So one of the sp2 orbitals is right here, making a bond to carbon. Another is right here, making a bond to this carbon. And the other one has to be holding the lone pair. If these electrons are sticking way out, as they are in this molecule, they can't be delocalized. So to be delocalized, they need to be next to p orbitals. You have to have lines of p orbitals like that are perpendicular. So that's another requirement that we have to think about. And all of these molecules that we've been drawing have had that. They've all had p orbitals that you can push electrons to. All right, so that is delocalized right there. Or not, that lone pair cannot be delocalized. What resonance structures could I draw, though? I couldn't draw this, but I could push these electrons here, and then these here, and then these here, just like benzene. So what would certainly be valid then would be this. And by the way, I'm not trying to get you to memorize every single exception. I'm just trying to get you to realize that there are exceptions because resonance makes things more stable. And if resonance makes things more stable, it's going to do that. It will delocalize to be more stable. There's no reason a molecule would want to become less stable. Okay, so how could I do the resonance? If I can't move the lone pairs, I can still move the pi bonds. By the way, this is the same pattern as here, pattern 5. Okay. So I can move the lone pairs here, these lone pairs here, and these lone pairs here. And I get an equivalent resonance structure. Again, meaning it's the exact same thing except just flipped. Okay, so those are two resonance structures about this. Pyridine. If you ever see a bottle of pyridine, go the other way. This smells like the worst thing you could ever imagine. There's nothing that you can imagine that smells this horrible, okay? I mean, dead corpses, not as bad, because it's a uniquely bad smell. And you know how you get songs stuck in your head that are awful? It's a smell that gets stuck in your head that never wants to go away. So yeah, usually when you see organic compounds with nitrogens, amines are generally have the smell of rotting fish at best, okay? There are exceptions, but amines are about as unpleasant as they get. Not always. A lot of our medications, acetaminophen, don't stink, but they're also covered in binders, so you don't smell them as much. Okay, chapter 3, I don't really want to get too far into because I just think you're all lectured out probably for the day. So maybe I'll talk about some things related to Lab 1, but there are things I do need you to get started to learn. I'll go back over the general details here. I'm going to rush through this first part for just a second. So acids and bases, you spent a lot of time in Chem 140 talking about it. And Bronsted-Lowry acids and bases are what we're mostly going to deal with in this class. The most simple definition of acids and bases was Arrhenius, and that was very important for Chem 140. Arrhenius acids and bases, if you remember, Arrhenius acids make what ions in solution? What ion do we always think of with acids?
OH or H.
H plus, yeah. Which is more correctly written as H3O plus, right? Okay. So an Arrhenius acid is anything that makes H plus in solution, and an Arrhenius base makes what very important base ion in solution?
OH minus.
OH minus, yeah. And it's also a very limiting definition because it says an acid has to make an H plus and a base has to make hydroxide. The next most broad definition is the Bronsted-Lowry definition. So when I say it's broader, that means it includes Arrhenius acids and bases, but adds others. And so we'll start with this here. An acid, according to Bronsted-Lowry, is any molecule that donates a proton in a reaction. By donates a proton, that means if we look at the before and after picture, an acid is losing an H plus. Okay. A base, on the other hand, is whatever is accepting the proton. Okay. I'm going to pause for just 1 second. Okay. Talk amongst yourselves.
Okay.
Okay. So anyway, we have here our base, our acid, our conjugate acid, and base. All right. I want to try the same reaction here. Only one of these is going to be more probable, as we'll see later on. But I want you to try the reaction as if this is the base and this is the acid. And then try writing the reaction as if this is the acid and the water is the base. Okay? So take a moment and try that. Okay, so if we were to go ahead and look, if this is the base, then we would form what? N. Oops, sorry, those are carbons. And we would now have 2 hydrogens. And the positive charge on the nitrogen, correct? Plus, on this side, we would lose one of the hydrogens. And so this guy right here, again, it looks kind of messy, so I'm going to write in CH3. Not required, but I think it looks better. This would be the conjugate, which? Conjugate acid or conjugate base?
Acid.
That's the conjugate acid. And then the hydroxide is the conjugate base. On the other hand, if we thought of it the other way around, if you think of the amine as the acid, this would give you a negative charge there and 2 lone pairs on the nitrogen. And then hydronium ion. So hydronium ion is what? The conjugate acid or the conjugate base this way?
Conjugate acid.
Yeah, that would be the conjugate acid. It needs a positive charge. And it's the conjugate base. Now, in reality, neither of these reactions are going to really work. This all comes down to equilibrium, okay? In both of these cases, the equilibrium favors the left. In the top case, it slightly favors the left. By slightly, I mean maybe 10,000 to 1. That's pretty significant. In the bottom case, it's unbelievably will favor the left. We're talking about on the order of, 1 with, like 15 zeros, 20 zeros for it. So, but that wasn't the point of the question at this point. The point was simply that you can draw both of these given that. And we'll worry about which way the equilibrium lies in just a moment. Okay, water is neutral. So does that mean it's neither an acid nor a base? The answer would be no. It means water can act as either an acid. And when's the only time it would really act as an acid? That would be in very basic environments. And if you want to replace the word environment with solution, that would be okay, but or as a base. But when's the only time water is going to act as a base? When it's around very strong acids, okay? But otherwise, it is pretty much neutral H2O. So you always want to think of H2O as having 3 identities, so to speak, depending on its environment. When water is around very strong bases, this is not very strong, it will tend to be hydroxide, right? It loses a proton. And when water is around very strong acids, this is not a strong acid, but if it were around hydrochloric acid, for example, it will exist as hydronium. If it's around neutral molecules, it just stays H2O. So water is very accommodating, is all that we're saying. It adjusts depending on its environment. So all this talk about curved arrows for resonance structures still applies when we talk about reactions, except now we can actually form bonds. This is the first type of reaction mechanism we're going to really learn: acids plus bases. A base, remember, accepts a proton, or instead of saying accepts, you could say steals. Okay, it is taking away a proton. An acid loses a proton. So this is the standard curved arrow pattern for an acid-base reaction. Okay. The curved arrows are no different, other than for resonance structures, it wasn't the arrows that were different, it was the rules that were different. The rules were you could not form you couldn't change the connections of atoms in resonance. Okay. Other than that, the arrows work the same. But now you are allowed in a reaction to change bonds. Okay. Because you agree these are not resonance structures. Okay, so this spells out the mechanism. Mechanisms are going to be incredibly important, starting with about exam 3 and going all the way to the end of the semester. They're typically 20 to 25% of every exam, so critical. Okay, they explain why reactions happen the way that they do. And so understanding how to draw curved arrow mechanisms, which includes resonance and includes using these curved arrows for reactions, is vital. It's going to allow you so much power in predicting why reactions occur the way they do. And we learn patterns that, basically say this makes sense and this does not. So the most fundamental of all the patterns really is acid plus base outside of resonance. So hydroxide, we know hydroxide is a strong base, right? And we know that acetic acid is a weak acid, but for organic chemistry purposes, it's quite strong. Compared to all the other organics, it's strong, but it's much weaker than hydrochloric or any of those. So how does this work? The base reaches out with its electron pairs, grabs the hydrogen. We can't stop there because now hydrogen would be exceeding a duet. Remember, hydrogen wants only one bond. So it has to let go of those 2 electrons, and they go to oxygen. So that is the pattern. Equilibrium strongly favors the right, which is why I have not drawn a double-sided arrow. But if we did do the reaction backwards, what would it have to be? It would be these lone pairs are grabbing what? They want to get one of the hydrogens. Does that make sense? It's not drawn in a way to really do that, but we have that right there. Okay, so let's take a look here at this reaction. If the amine here is the base and water is the acid, what's going to happen? Where is the arrow going to start? Coming from the lone pair of the base or the lone pair of the acid?
Lone pair of the acid?
Look at the pattern above. Lone pair of the base. Okay.
All right.
Starts at the lone pair of the base and grabs a proton away from the acid. Okay, so we can go like this, and they don't have to be in fancy curly cues or anything, but I'm going to go over the hydrogen. It's kind of ugly. And it will grab that hydrogen. Or rather than hydrogen, I should say proton. And then hydrogen has to let go of these 2 electrons. We call that heterolytic cleavage. I talked about that in chapter 2. That means the electrons all go to the oxygen. Hydrogen gets none. Hydrogen is losing those 2 electrons in exchange for gaining a bond to the nitrogen. Okay, so now what's left over here? The nitrogen now has, instead of a lone pair, it has a bond to that second hydrogen. And those are all supposed to be straight lines. Okay. Oh, by the way, I see this sometimes. Never do this. Never, never, never. Okay. Because now it looks like, where are those going? Are those going to a carbon? Because remember, an intersection is supposed to be a carbon. That makes no sense. Okay. They have to go directly to the nitrogen. Okay. And what do we have over here? We now have oxygen with hydrogen, and oxygen is keeping the lone pairs. Okay. And we already labeled these as conjugate acid and bases earlier. The hydroxide is the conjugate base. The amine here, the protonated amine, is the conjugate acid. Okay. This next reaction we will learn in chapter 8 or 9. It's called the elimination of alcohols, or dehydration of an alcohol. I want to look at these steps. There are 3 steps here. Each one of these is a step. Which ones are acid-base? Meaning either gaining a proton or losing a proton. I don't care which one it is. It just has to be gaining or losing a proton. In the first step, is this gaining a proton? It is. Yeah. Oh, by the way, the other way we can call this is proton transfer. Acid-base, proton transfer. A proton is moving from one chemical to another. Okay, so this is acid-base. So step 1 is definitely an acid-base, also called a proton transfer. Is step 2 acid-base?
No.
No, it's loss of water here. Okay, so step 2 is something we haven't learned yet, called loss of a leaving group. Water picks up its electrons and says, I'm leaving you. So not acid-base. That's the only thing that's important. Step 3 is something gaining or losing electrons. I mean, a proton. And you'll notice that water is taking that proton. So therefore, this is an acid-base. Okay? Or you could say this compound is losing a proton. Okay, it is acid-base. And as I said a moment ago, later on I'll change the name from acid-base to proton transfer. It turns out in reactions there's only so many possibilities here. Acid-base, loss of a leaving group, substitution, a few others. All right, and the last section I wanted to cover today is going to be section 3.3. We are mostly going to be looking at what we did not cover in Chem 140 in this class. We are mostly going to be looking at qualifying acidity. So in Chem 140, we spent tons of time talking about buffers, talking about, which way does the equilibrium lie, all of that. We're going to be more interested in why something is more acidic or less acidic or more basic or less basic in this class. It's much more exclamation based. All right. So from general chemistry, how do a strong acid differ from a weak acid? What is the difference? What does it mean to be a strong acid versus a weak acid? What does strong mean? That's the important word.
Like further
Dissociate.
Yeah, it's dissociation, right?
Mm-hmm.
Strong means totally dissociates in solution. Like, we'll say usually much greater than 99% in solution. So for example, HCl plus water. This is very strong. So that means it forms pretty much exclusively H3O plus and chloride. There's almost no equilibrium. It goes very far to the right. NaOH in water becomes Na plus ions and hydroxide ions. Mathematically, we would express the top reaction by saying Ka is much greater than 1. Remember that the equilibrium constant for acids, it lies very strong to the right. When I covered this last semester, I don't usually write the water in. I usually write it as just H plus, but it's sometimes more convenient in organic chemistry to write it as hydronium, and so that's what I'm going to do. Which K is this one? A solid dissolving. Which K is that?
KS
KS.
P.
Good. Or it could be KB is much greater than 1, but we didn't have any KBs much greater than 1 in Chem 140. We don't see any of those until this semester. But the idea here is there's almost no equilibrium. You put HCl in water, you don't have HCl anymore. You have hydronium and chloride. You put sodium hydroxide in water, you don't have sodium hydroxide, you have sodium ions and hydroxide ions. Okay? That's pretty much what that means. So quantitative comes down to using these Ka and pKa values to compare the strengths. All right, now you'll remember from last semester, the way that we quantify Ka values, I should have gotten rid of this line. Shoot. Anyway, is that we look at this equilibrium right here. And or this equilibrium. And that's how I cover it in general chemistry. I use it this way. I leave out the water. Okay. I'll stick with this way though for us here. This is the Ka, the acidity constant. What never appears in K? What is the only thing that appears in Ka? terms which are
aqueous.
aqueous. Good. Water is left out because its concentration is constant. Except in very, very concentrated solution or very dilute solutions or very concentrated ones, water's molarity is always about 55. You can prove that. No one will ever ask you what is the molarity of water, right? Because you only know the molarity of solutions, but you can prove the molarity of water is always about 55. And since it's a constant, we leave it out. This is Ka. So you should remember that from last semester. Ka values almost always have 10 to the powers in them, right? So for example, the Ka of acetic acid is 4.5 times 10 to the minus 5, or 1.8 times 10 to the 1.8 times 10 to the minus 5. Okay. And they're ugly numbers because of that. We don't like dealing with them in organic chemistry. So in organic chemistry, instead of dealing with Kas, we deal almost exclusively with pKas. Okay. So Ka values can range from 10 to the negative 50 to 10 to the 10. If an acid is strong, what does that mean? Ka is the stronger the acid, the larger the value of K. The weaker the acid, the smaller. In Chem 140, what do we never worry about the Kas of? We never worried about the Kas of strong acids. Because remember, we said what? They totally dissociate, and we didn't worry about it. We just said the Ka is much greater than 1, and we left it at that. On the other hand, in Chem 140, here's my Chem 140 notes. You'll recall I gave you all these tables for weak acids, okay? And you saw that they're never negative, but their power of 10s are negative, right? These numbers are all much less than 1. Okay. Now, instead, we like to deal in organic chemistry with pKas. If you remember pH and pKa, P means negative log base 10. So if we go ahead and deal with these, the pKa values will range from negative 10 to 50. Since a P means you put a negative sign in the front here, it's going to flip the way this goes. So the strongest acids have the lowest pKa values. Okay, typically less than 0. The weakest acids have very high pKa values. For reasons that we'll get into later, any value which is less than 0 should be treated with suspicion. But the idea is if a pKa value is less than 0, that means it's a very strong acid, or it's a strong acid from the way we taught it in 140. So hydrochloric acid will have a pKa value. Hydrochloric is strong, its pKa value will be less than 0. Okay. Nitric acid is the weakest of the strong acids, but if it's a strong acid, its pKa will be less than 0. Okay. Now, You will need to memorize these. I just put a handout on the website. And I know you're going to go, oh my God, is he serious? Yes. Okay. On page 230, I added a section called Handouts under the course notes. You need to know the table that says pKa table memorize. You do not need, and in fact, do not even begin to memorize Dr. Evans' table from Harvard, okay? I just give that for reference. So, how do we learn them? We only need to worry about approximate values. The approximate values will always be based on intervals of 5. So less than 0, less than or equal to 0 would be better. 5, 10, 15. There's none around 20 that we need to know now. 25, there's none around 30 we need to know now. 35, 40, 50. Okay. So all the very strong acids that were inorganic, hydroiodic, hydrobromic, anything on the strong list that you learned in Chem 140 has a pKa of less than 0. I do not need you to know specific values. I only need you to know they're less than 0. Sulfonic acids we have not talked about, but who is their closest cousin on this list? They almost look the same as what very important acid? If I covered up the R, that would look a lot like which acid?
H2SO4.
H2SO4, sulfuric acid. So sulfuric acid and its cousin, sulfonic acids. So this R could be what? It could be CH3. It could be a benzene ring. It could be anything carbon, okay? Their pKa's are about usually -2 or so. Sometimes it's much more. But less than 0 is all that I care that you know. Hydronium, or anything that looks like hydronium, is around 0 or less. Okay? Anything that looks like hydronium means O with a positive charge. You see, that's what these all have in common. O with a positive charge. Any hydrogens on an oxygen with a positive charge, the pKa will be 0 or less. So the first one is hydronium. The second one is a protonated alcohol, meaning someone took an alcohol and added a hydrogen to it. This one is a protonated ether. I should have written the word protonated ether. And this is a carboxylic acid that someone has protonated. What's the only way you could make a carboxylic acid act as a base? You'd have to add it to one of these really, really strong acids. So these really, really strong acids will actually protonate a carboxylic acid. Okay. So those are, when we say strong acids, this is really what we mean, less than 0. Okay. Carboxylic acids have a pKa of about 5. That means their Ka's are what? 10 to the -5. Okay. Pyridinium, and this is a handout. You don't need to write this all out. It's on the website. Okay. I don't really need you to memorize carbonic and hydrozoic acid. Those two aren't really important. Ten would be phenols. Now remember how 0 we said protonated oxygens where the oxygen was plus? You'll notice you have the same idea here with nitrogens. The only one that was special was pyridinium. And you don't need to really know its name, but anyway. Don't worry right now about peroxides or peroxycarboxylic acids. They're not really important. Thiols, definitely no. These two aren't that big a deal. In fact, let me just take this for a moment. And let me just highlight which ones you really do need to know by memory. Okay. The ones you really need to know by memory are going to be these, these, carboxylic acids, these two, phenols, ammonium ions, anything protonated there, thiols. Uh, 15, water, alcohols. And then all of these are important. The most important things to note about amides is amides are not, what are they not? They are not amines, which means they are not basic. If anything, they are extremely weak acids. In other words, where are amides on the table? They're 15. Where are amines on the table? They are 40. Okay. The other extremely important rule that we will get into is the strongest bases give the weakest, the strongest acids give the weakest conjugate bases. So if HI is the strongest, actually HClO4 is the strongest acid of all of these, then ClO4 minus is the weakest base, okay? So the strongest acids produce the weakest conjugate bases. Alkanes, you would never call an acid. But carbanions, like for example, this compound right here, okay, first of all, what is the Ka of that hydrogen? Of any of these hydrogens, that's an alkane. So what's its pKa? Its pKa is, where are alkanes? They are 50, okay? So these are the weakest acids you can imagine. So that means its conjugate base, take away the proton. It takes a lot to remove that proton. And so this is like about as vengeful as it can get. It wants that proton back. So this is about as strong as a base as you're ever going to deal with, okay? And as I mentioned, if this stuff is in a syringe, it won't dissolve in water because it would attack water instantly. So it will, I mean, it would dissolve in water, and that's going to be the point. A solution of this dissolved in an alkane, the instant it even comes into contact with air, it will burst into flames, okay? It will so violently attack any water in the air to take that hydrogen back. So that's the idea. The weaker the acid, the stronger its conjugate base. This is the absolute strongest conjugate base you can get. And similarly here, the stronger the acid, the weaker the conjugate base. So ClO4 minus is about as weak a base as you'll ever get. So that's how it always goes. Strong acids, strong bases are opposite ends of the table. Who's right in the middle? Water, so to speak. because it can be both. To give you an example of a typical question that you will see on the exam, one that I will always ask is something like this. Just to make sure you know them. I'll pick usually 10, 8 to 10, and ask you to tell me their values. Meaning I want 0, 5, 10, 15, 20, whatever, you know, there. So H2O was 15.
15.
What would this guy be? This is what kind of a compound?
Alkyne.
It's a terminal alkyne, meaning it's got a hydrogen on it, and alkynes are 25. Okay. What is this kind of a compound right here? That is a
Hydrocarbon.
yeah, and since there's no functional groups, it's an alkane, right? Alkanes are about 50. So that means this is by far the least acidic of all of these guys that I gave you. I lied. I do want you to know sulfonic acids. Sorry. Okay. So for this one, you could write 0 or less than 0, and I would be happy. All right, so make flashcards. These really don't take that long to learn. And that's, you know, memorization questions are usually the easiest ones. They don't require much thinking. All you have to do is say what functional group that is, and then there you go. Be very careful not to mix up amines and protonated amines. What's the pKa of ammonia? It was 40. Not acidic at all. The pKa of protonated ammonia, which is ammonium ion, is what? About 10. So that's a common mistake, is people will mess those two up. They'll get them switched. What kinds of charges are more likely to occur at high pKa's? You're more likely to get positives at these lower pKa's in acids, and vice versa. You're more likely to get negatives when you have bases.